Okay, let's continue chapter 8 on proofs involving sets. We're going to look at 8.3, proving that two sets are equal. The other day I mentioned that, for two sets to be equal, that means they have the same exact elements in them. So to break this down into a proof, we actually, if we can show that A is a subset of B and show that B is a subset of A, then we can conclude that the two sets are equal. That's one strategy to show probably the key strategy to showing the two sets are equal. Okay. So in other words, you take an arbitrary element of A and show that it's in B, and then you take an arbitrary element of B and show that it's in A. So then they must have the same stuff. Okay. So here's the first example of this type of proof. So I've find two sets A and B. Okay. I'm going to show that A equals B, where A is a set of even integers, and B is a set of integers that can be written as the sum of two odd integers. Okay, so X, set of X, such as X equals A plus B, for some odd integers A and B. Okay? So here's the proof. So first I'm going to show that A is a subset of B. First, we will show A is a subset of B. Okay? So as we learned, to show that A is a subset of B, you take an arbitrary element of A, and using just the fact that it's in A and then any other given information, show that the element is also an element of B. So we need to take an arbitrary element of A, therefore that arbitrary element is just going to be an even number. Okay? So we start out, let that little a be an element of capital A. Okay? Now what we know that A is even.
Should we use the little a since the little a is a part of B, telling that it's odd? Or is it not going to matter?
Well, yeah, I mean, I can see how you might not want to include. You could use X. Yeah, I mean, that's kind of a good rule. But don't use an arbitrary letter that's used in the statement. I mean, just so that's probably a good idea. Let's just use X. So it's arbitrary element of A. What I need to do is show that X, since X is in A, I need to show that I can write X as a sum of two odd integers. Okay, I could end up using A and B, but all right. So let X be an A, then X is even. So then X equals 2n for some integer n. Right? Definition of even. Well, I need to write this as the sum of two odd integers. Well, here's how. So then X equals 2n. I can write it like this. 2n plus 1 is clearly an odd integer. What odd integer do I think I'm going to add to this? So 2n, I added 1, I better subtract 1. This is a common trick in math. You have a quantity, you want your quantity to look different. A lot of proofs in calculus, you see this, you add and subtract the same quantity, so that the net result is 0 change. So 2n is equivalent to 2n plus 1 plus negative 1. Okay? Clearly 2n plus 1 is odd. We know negative 1 is odd. Do I need to say that? I need to prove that negative 1 is odd? So since 2n plus 1 and negative 1 are odd integers, X is an element of B. I don't really need to restate that they're. I just need to show that X is the sum of two odd integers. 2n plus 1 is not integer, and negative 1 we know is not integer, so X is in B. All right. So now so therefore A is a subset of B. Thus A is a subset of B. Okay. Any questions
2n plus 1, would we use another letter than n?
You don't need to. I mean, that's what, because the definition of an odd integer is it looks like 2 times an integer plus 1. So this is exactly the right form. So this is an odd integer, and you know, I didn't really prove the negative 1 is odd, but for known integers, I mean, we know that negative 1 is odd. Okay. Any other questions? All right. So the second half, second, we show that B is a subset of A. Okay? So the proof goes, you take an arbitrary element of B, and then show that it must be also an element of A. Okay? So let X be an element of, I don't know, let's use Y, just so I use Y. So let Y be an element of B. By definition, it can be written as a sum of 2 odd integers. Okay. Then Y equals A plus B for some odd integers A and B. Okay. I need to show that Y is even. Okay. Well, now basically just showing that the sum of 2 odd integers is even. So I need to use the fact that these are odd integers, right? Use the definition of odd integer, and then when I combine them, I'll get when I add them together, it should look even. Then A equals 2m plus 1, and B equals 2m plus 1 for some integers. M and N. Okay. And Y, which equals A plus B, equals 2n plus 1 plus 2m plus 1, which can be written as 2 times the quantity n plus m plus 1. Right? Because I have a 2n, I have a 2m, and then 1 plus 1 is 2. So I can factor out a 2. Yeah. And, I mean, you could, you could add more details. You could say equals 2k for some integer k, which is n plus m plus 1. But I'm just going to say, so then Y is even. Y is even, and therefore Y is an element of A. Thus, B is a subset of A.
Do we have to say that A is a subset of, or is it the next part where we just like conclude the whole thing saying that A?
Well, yeah, you could say therefore A equals B. I mean, it's, or you say since A is a subset of B and B is a subset of A equals B. But I mean, we're basically done. I mean, once we've shown, and we know we're trying to show that A equals B. So the only thing you have to show is that A is a subset of B and B is a subset of A. Alright, it would be, you could say, plus A equals B. We want to. Okay. Any questions? So the strategy is, the important thing here, right? That to show the two sets are equal, you can prove that A is a subset of B and show B is a subset of A. That's the keys to the proof. Okay, good. And the proof. All right. I'm going to show you, the next couple proofs, I'm going to show you a couple of different techniques to show two sets are equal without really breaking it down in this way, into two halves. Okay? So let's look at these. Here's this statement here. Prove this statement. If A and B are sets in a universal set U, then the complement of A union B equals the complement of A intersect complement of B. So if we're going to use the technique I just used, you might show that this side is a subset of this side, and this side is a subset of this side. What's a little bit difficult is that we're using complements here. Complements are kind of like negative statements. Like instead of saying X is an element of complement, I mean you're really saying X is not in A union B. And we know we have clear definitions for what A union B means. So saying something that's not in A union B is a little bit more complicated. It's not in A and it's not in B. So I'm going to show you another way you can prove these two sets are equal. I'm going to start with this set, and I'm actually going to use the definitions of the complement and the union to rewrite this set in set builder notation. And I'm just going to use chain of equalities to rearrange the set builder notation until I can write the set builder notation as the definition of this set. Okay, here's how the proof goes. So I'm just gonna have a chain of this set. I'm gonna start with this equation, this set, and I'm just gonna have equal sign, and I'm gonna keep writing stuff until we equal it. Sorry?
Is it basically De Morgan's law?
Yeah, we're using definitions and De Morgan's law, right? So definitions of this, definitions of the negation and statements and or statements and De Morgan's law, right? So there's all these little kind of justifications along the way. Okay. All right. So A union B complement. All right. The other day I reminded you what it means to be in the complement of a set, or the definition of a complement of a set. It said that the complement of any set is the universal set, the difference of the universal set and the set that's being you're taking complement of. So that's the definition of the complement. It's everything in the universal set that's not in A union B. Okay? Now, when we have a difference, using the definition of a difference of two sets. This would be the set of all elements in U that are not in A union B. So I'm going to write that in set builder notation. So it's a set of arbitrary elements X. We don't even know what these objects look like. We're just going to call it X. Okay, but I know that X is in U. X is in the universal set, and X is not an element of A union B. Okay, if you think about it, every equation should be clear. Like, how does this equal this? Well, I'm using the definition of complement. I'm sorry, of the difference, the set difference. Okay. All right. Now I'm going to use just different notation. Instead of saying that X is not an element of A union B, I'm going to use the negation. And I'm going to say this is it is not the case that X is an element of A union B. So this is a set of X such that X is in U, and it is not the case that X is an element of A union B. Okay? So those are equivalent statements, saying that X is not an element and saying it is not the case that X is an element. Now I'm going to unravel this. What does it mean that X is an element of A union B? This means that X is an element of A or X is an element of B. And you can see where that De Morgan's law is going to come in I'm gonna have a negation of an or statement, and I'm gonna unravel that using De Morgan's law. All right, so this is the set of x, such that x is in U, and it is not the case that x is an element of A or x is an element of B. Okay, let's use De Morgan's law. So the negation of this and statement, I can negate both statements and change this to an and. Right? So this is De Morgan's law says this is the set of x, such that x is in a universal set, and parentheses x is not an element of A, and x is not an element of B. Okay? That's De Morgan's law. All right. Now I'm gonna kind of break this up into, I'm kind of distribute this statement, saying x is in U and x is not an element of A, and x is in U and x is not an element of B. So I can break this up and I'll get the statements with these two complements. So there's a set of x such that let's put parentheses here. So x is an element of U and x is not an element of A, and x is an element of U, and x is not an element of B. I'm going to rewrite this. I'm going to break this up into the union of two sets. Set of x, such that x is in the universal set, and x is not an element of A. Is this set, okay, and it's going to be, so x is in here and in here. So using intersections, that's the same as saying x is in this set, intersect x such that x is in the universal set, and x is not in B, okay. So the reason I did that is so it looks like what I want. I want it to look like A complement intersect B complement. So here's, x is in A, this is equivalent to, A complement, this is like my B complement. So I'll make it into a union. Use the definition of a set difference. This is the same as the set U minus A. The set U minus A is the set of all x's that are in U and not in A. Intersect U minus B, the set of all x's in the union and not in B. But this is the definition of a complement intersect B complement. So this technique, it's there's a lot of justification along the way. Each little step, you might even it might be nice to even write a justification. Some people, maybe write some words above the equal sign. Some people will write their chain of equations on the left, and then maybe to the right they'll have like a column with justifications. So here I use the definition of complement. Here I use the definition of set difference. Here I use equivalence of these two statements. And I use just definition of a union. I use De Morgan's law. Broke this up into a distribution. I did a distributive of an and statement. I used the definition of intersection, the definition of set differences, and then the definition of complement. So, complement of A union B equals complement of A intersect complement B. All right, any questions? I'm going to show you another technique called a biconditional proof. which is more like the last one I did. I'm going to show, in the next type of proof, I'll take an arbitrary element of this and show it lives in here. But then, if you just read the proof backwards, that'll take this arbitrary element here and show that it's in here. So it's called a biconditional proof. Instead of equal signs, I'm going to have if and only if statements. Okay. Following proof, following is what I call a biconditional proof. I'm going to be proving both directions of an if and only if statement at the same time. Okay, so this following is a biconditional proof, a chain of if and only if statements, or biconditional statements. To show A is an element of, what did I say, X is an element of A, if and only if X is an element of B. Okay. So I'm going to show that the set A and B are equal. And I'm going to start with an arbitrary element of A. As you read the proof forward, you'll prove that X is in B. And then if you read the proof backward, X is an element of B, and the reverse implications prove that X is in A. And so I'm really showing in one proof, I'm going to show that A is a subset of B and B is a subset of A. Okay? But it's a little shorter because I don't have to write like one proof. All right, here's the statement. So A, B, C are sets. Prove that A intersect B union C equals A intersect B union A intersect C. So remember, to show these two sets are equal, I'm going to show this is a subset of this. I'm going to show that this is a subset of this, but I'm going to do it on one proof. All right. So instead of starting with words like let, I'm just going to say X. The statement X is an element of this set. X is an element of A intersect B union C. Okay. For a biconditional proof, you really can't use words like let or assume because that implies that you're going in one direction. So this is true. X is an element of this set. That implies, and I'm going to come back and change this, but let's think about the forward direction first. If X is an element of this set, then that's the same as saying that X, what is the definition of an intersection? That means that X is an element of A and X is an element of B union C. Okay? I'm just using the definition of intersection. Right? X is in this intersection, that means X is in A and X is in this set. Alright? Now I'm going to break up this right here. What does it mean for X to be in the union of B and C? It means X is in B or X is in C. So that implies X is in A and, parentheses, X is an element of B or X is an element of C. Okay, so we prove distributive laws. Back when in chapter 2, we're talking about logic. So I can distribute this and statement, so I get this implies that X is an element of A and X is an element of B, or X is an element of A and X is an element of C. Okay, so the distribution law we proved in chapter 2. Let's use the definition of intersection here. So if x is in A and x is in B, that implies that x is an element of A intersect B. Or, okay, so x is an element of A intersect B, or, using the definition of intersection again, x is an element of A intersect C. Now, if x is in this set or x is in this set, I can use the definition of union. So this tells me that x is an element of the union of these two sets, A intersect B with A intersect C. And that's what I wanted. So if you read this proof, I start with an arbitrary element of the left-hand side, and I show that that is an element, also an element of the right-hand side. Right? So this proof shows that the left-hand side is a subset of the right-hand side. Now, I'm just going to add the other side of the arrow to make these if and only statements. Because I can read it in reverse. Suppose x, you start with this. X is here. That implies that x is here. X is an element of A union B, or x is an element of A intersect C. But that, I'm going to use the definition of intersection to imply that x is an element of A and x is an element of B, or x is an element of A and x is an element of C. And then by distributive law, that implies that x is an element of A and, in parentheses, x is an element of B, or x is an element of C. By the definition of a union, that implies that x is an element of A and x is an element of this set. By the definition of intersection, that implies that x is an element of A intersect B union C.
So the steps undo each other when you go backwards.
Well, so not only does this imply this, but this also implies this in every single step. So they're really if and only if statements. Because think about it, we talk about definitions are always if and only if statements. So that's really all I'm using here is definitions. I'm using definitions of intersection, definitions, well, we did use distributive law. So we did intersection, we did definition of a union. Here we did the distributive law, but that's an if and only if statement. And so you're justifying, so you can actually read this proof in both directions. And each step implies the previous, and each step implies the next one. So they're actually if and only if statements. So what I've shown is that if x is in this set, x is in this set, if and only if x is in this set. So they must have the same elements. So I might say one more sentence. Thus, A intersect B union C equals A intersect B union A intersect C. Okay. So instead of using the properties, basic properties of showing that two sets are equal, you actually can do it in one biconditional proof. Okay. If you read it forward, that shows that the left-hand side is a subset of the right-hand side. If you read it backwards, that shows that the right-hand side is a subset of the left-hand side. Okay. Any questions? Okay, so that finishes up chapter 8. Okay. And so I want to do, we have time for just one section of chapter 9. This is chapter 9 is on. So we've been proving statements, right? You've been prove this, prove that. Chapter 9, you're going to be disproving statements. This happens a lot. I mean, oftentimes very complicated mathematics. I mean, people have what they call conjectures. A conjecture is like you're a candidate for a theorem. Like you think, we're pretty sure this is true, or a mathematician might say, I'm pretty sure this is true. I don't have a complete proof yet, but like I've worked out 1,000 examples and it's always true. So my conjecture is this statement is true. Okay, so but it only takes one person that comes up with a counterexample to prove that that statement is wrong. Okay, and so in history there have been people who have conjectures and they have theorems, and then down the road somebody finds a counterexample that shows that actually the statement was wrong. Okay, so that's kind of the idea of chapter 9. Chapter 9 is about disproof, and I'm just going to focus on section 9.1, where so a disproof is we're proving a statement is false. Okay, so to prove a statement is false, often the simplest way to prove a statement is false is with a counterexample. A counterexample is just an example that shows a statement is false. Okay, that's really just the purpose of a counterexample. You know, somebody makes a claim, or somebody makes a conjecture, or even someone presents a theorem, and you can say, well, actually, you didn't consider this counterexample. This just shows that your statement is wrong. Okay, so section 9.1 is on counterexamples. Okay. So a counterexample is an example that disproves a statement. Okay, so I'm going to show you some examples of, in the homework, you have statements that you have to either prove or disprove. So to disprove them, it can be as simple as giving one counterexample. Okay, so here's a statement. All prime numbers are odd. So is this true or false? False. How would you convince somebody that this is a false statement? The number 2. So number 2 is really the only counterexample you could get. So here's a disproof instead of a proof. Here's a disproof. So consider the counterexample example 2. So 2 is both a prime number and even. Therefore, the statement is false. Okay. So if there's a statement that's a universal statement, all prime numbers are odd. All you have to do is show one counterexample. There's one example that proves that this statement is false.
Whereas it says there exists some number, then you have to show that all numbers.
Yeah, exactly. If there was there exists proof, then you'd have to show that its negation is true. So that's there exists. Right? So they're all for all, right? So the negation of if I said all prime numbers are odd, if I claim that's false, then the negation is there exists a prime number that is not odd. There exists a prime number that is even. Okay. So that's how we use the word counterexample. A counterexample is just an example that sometimes it's not obvious. I mean, sometimes mathematicians will have a theorem that works most of the time, and then somebody comes up with maybe with a computer or something, doing simulations or something, that they find a number that doesn't work. Okay. So, any questions so far? I'll give you a couple more examples of how do you, examples of disproving a statement using a counterexample. Again, sometimes the counterexample that works isn't so obvious. I mean, the number 2 is obvious, and for that last statement, and it's the only counterexample, and it's the only prime number that's not prime. I heard, someone say sometime, I mean, so really, like a physicist or somebody, a scientist would believe this statement, they would just say that this is, experimental error. Just forget about it. This is really a true statement. Not mathematicians. Okay. So let's disprove the following statement. For sets A, B, and C, the difference of A and set B intersect C equals, so you might think, like with if this was a union, you could kind of just use this like distributive law. So you might think, well, maybe I can distribute this, and this is the difference of A and B intersect the difference of A and C. So this is actually false. So if you sat here, and tried to prove this statement, you might try to use like one of those biconditional proofs, like you might take an element here and show it lives there. You might get frustrated because it's actually not a true statement. Okay? So here's a disproof. Consider the following counterexample. Okay, so all I need to do is produce one example that shows this is false. So I'm going to define a set A, B, and C where this does not equal this. So that'll disprove the whole statement. All right. So let A be the set containing 1, 2, and 3. B is the set containing the numbers 1 and 2. C is the set containing the numbers 2 and 3. Okay. So this counterexample will show that the left-hand side is not equal to the right-hand side. All right. So let's do some more work here. We got to show that they're not equal. So A minus B intersects C. Well, A is this set. B intersects C is what set? The set containing the number 2, because that's the intersection of B and C. So the set 1, 2, and 3, the difference of set 1, 2, 3 and this, so I take away the number 2. So this should equal the set of just 1 and 3. Okay? But the right-hand side, so A take away B, well, A is 1, 2, and 3, and I take away number 1 and 2. That's the set just with 3 in it. Intersect A minus C, so if I have 1, 2, and 3, and I take away 2 and 3, I'm just left with the number 1 in this set. Okay, so this is the set containing 3, this is the set containing 1. So what's the intersection of these two sets? The empty set. So clearly the left-hand side and the right-hand side are not equal in this equation. So thus A minus B intersects C is not equal. Oops. A minus B intersects A minus C. So there's no distributive law when it comes to set differences. Can't do that.
So could we not show a Venn diagram to disprove it, or no?
Well, no. That's you know, again, not for mathematicians. So now you're talking to, you know, psychologists or something. One of those soft sciences. Or you're talking to a room full of college algebra students or something. But now, what's a Venn diagram good for? It's good for, I mean, you could probably be convinced of that just by looking at a Venn diagram, even though it wouldn't give you an actual proof. I mean, but that's the idea. You know, you can look at Venn diagrams and say, well, how can I write this you know, one way, and then I can write that another way, so those sets must be equal. That's kind of how we did it when we looked at Venn diagrams. We looked at, you know, I said, draw the Venn diagram of this, draw the Venn diagram of this. Do you think these two sets are equal? And we didn't actually prove them. But now we know how to, we can prove two statements are equal, and we can actually show that two sets are not equal as a counterexample. One more example for 1.1. Disprove. All right, so for integers, let's say for all a, b, c, they're integers. If a divides b times c, then a divides b, or a divides c. I already said disprove it. I mean, do you believe that's a false statement? I mean, the way you would convince yourself that it's false is with a counterexample. You try to come up with an example, counterexample of, you know, numbers a, b, and c, where a divides b times c, but a does not divide b and a does not divide c. That's really what we need. Consider the following counterexample. Everybody come up with one? Counterexample? A divides the product, but it doesn't divide any of the factors.
If A is 6 and B is 3 and C is 4.
Good. Did you say 4?
Yeah.
Yeah. I was going to say, the counterexample I came up with is A is 6, B is 3, and C is 2. That would work as well. But this works just as well. So, does A divide B times C? Okay, well, what is B times C? 3 times 4 is 12. Equals 6 times 2. Right? So 6, so clearly A divides B times C. Right? 6 divides B times C. But, I mean, 6 doesn't divide 3 because 6 is bigger than 3. 6 doesn't divide 4 because 6 is bigger than 4. So, but 6 does not divide 3, and 6 does not divide 4. So, we're done. So we found integers, an integer that divides, an integer A that divides B through C, but A does not divide B and A does not divide C. Any question about that? So it's a compound. Okay. That wraps up chapter 8, and sorry, chapter